Quantemol started with just doing cross-section calculations, but then got contact with the plasma community. So he also moved into plasma simulation and chemistry set design. And Matt showed the part of the cross-section calculation, which are vital parts of plasma or setting up plasma simulations. But in order to get a kind of really suitable simulation, you of course also need not just cross-sections for one species, but you need a whole set of reactions, including electron collisions, but also reactions between heavy particles. And I'd like to show you how you can use QDB and associated tools to quite quickly assemble and optimize plasma chemistry sets for your specific simulations. And to give you maybe just small motivation on why you want to do simulations and why you need good chemistry set data. If you want to simulate a plasma process where you usually have here a plasma in which you generate ions and neutral radicals, which then diffuse to the surfaces, react there with the surface, and then you get, for example, these such etching profiles. And of course, what you want to achieve in the end is you want to find the process parameters like power, pressure, or gas flows, with which you can quickly etch profiles which also have the shape you want to. For example, you want to have a most uniform trench here with as not a lot of defects, and you also want this to be kind of uniform across a wafer. And this then in the end depends on the fluxes of these radicals and ions, and also on the ion energy, on the angle they impinge on the surface, and all these are kind of parameters which you can't measure easily. And so the simulations help you to get a better understanding of the processes inside the plasma. And also it is a tool which you can then optimize your chemistry sets in addition to doing experiments. And of course, when you want to do simulations, you need a kind of robust setup. And usually these plasma simulations consist of two parts. There's the physical model, which essentially is the set of equations you solve to get your species densities, fluxes, the electromagnetic fields. And there are several options available. You have here, for example, the PIC simulations, which are quite accurate, but also take a long time and use a lot of computational power. And this is commonly used as the fluid approximation, which is faster, but where you use some information. So for some process parameters, doing a fluid simulation is well enough. For others, you might need the more accurate PIC simulations, or what is also, with the hybrid simulations, which combine different approaches, for example, for different species type. And the other thing you need to consider is the dimensionality. We can go from global, so 0D, which are very fast, but where, of course, you don't have a lot of information about the geometry and particle transport. So they give you a kind of good overview about which species are created in a specific gas mixture at a specific process parameters. But if you want to get actually accurate fluxes or energy distributions, you usually need to increase the dimensionality up to 3D, depending on how many of your geometrical characteristics you need to include to get an accurate enough picture of what is happening in the discharge. Because the other part then is the chemical model, which describes the chemical reactions in the plasma between the different species, so between electrons, neutrals, ions, and such. And it doesn't matter how good your physical model is, if you don't have a good chemical model, you won't get good results. And essentially, you have two kinds of discharges: the electron impact collisions and the heavy particle collisions. And as Matt already, you've seen in Matt's presentation, there are a lot of different electron impact collisions. You have momentum transfer, which usually governs the electron transport, for example, the diffusion, or it's also an important part of neutral gas heating. You have excitation and dissociation, which determine the density of excited state or dissociation products. You have the dissociative attachment and electron detachment, which gives you the amount of negative ions you have in a plasma, which can influence the discharge quite significantly. And you have then ionization and recombination, which determines how many electrons and ions you produce or consume inside a discharge. And of course, all these different cross-sections influence the discharge in different ways, and they can have quite important consequences. To give you an example, here on the left-hand side, you see this is a very simple argon model. And on the left-hand side, we simply varied the rate coefficients or cross-sections for excitation. And on the right-hand side, we varied the rate coefficient for ionization. And you actually see what's plotted here is then the electron density for different values of the excitation or ionization rate coefficients. And you see they actually both influence the electron density quite significantly. And you actually see that the excitation rate coefficients actually have a larger influence on the electron density than the ionization cross-section. This goes via the electron energy collisional losses you get via the excitation processes. So sometimes in plasma physics, you see that often in plasma physics, things are not always straightforward because these excitation cross-sections, they don't produce electrons directly, but they still have a big influence on the electron density via these collisional energy losses. And you also, if you look at the electron temperature for the same setup, you actually see that here it's not the excitation doesn't influence electron temperature at all, but it is mostly governed in this case by the ionization rate coefficient. And if, for example, you have, it's kind of varies, if you have a kind of reactive plasma and this electron temperature varies in a region where, for example, dissociation cross-sections are sensitive to changes in the electron temperature, this can give you quite a different neutral densities. And the same goes, for example, for dissociative attachment. You see some examples of CF4 and O2 simulations, where in one case we didn't include negative ions, and in the other case we did include negative ions. And you see in general that including the negative ions can lead to quite larger electron temperatures. And again, if, for example, the dissociation rate coefficients are very sensitive in this region, this can give you a lot higher degree of dissociation than the case without negative ions. So as you can see, having good data, including all important electron collisions and having good cross-sectional data is vital to get accurate electron densities, temperatures, and via this radical densities. And of course, apart from these electron impact collisions, you also have heavy particle collisions, which you can roughly kind of categorize into these parts with, for example, ion-ion recombination, which is usually the only loss channel for negative ions. So these will then again impact the electronegativity. You have charge exchange, both symmetric and asymmetric. So symmetric would be between an ion and its neutral counterpart, asymmetric between an ion and some other neutral. And this can then, for example, mix up your relative ion densities, which might be important for surface processes directly in case different ions induce different reactions on the surface, but it might also indirectly influence electron density and electron temperature, for example, because you get a different ion mean mass and therefore different diffusional losses. Another point is, for example, again, electron detachment, where a neutral collides with a negative ion and strips off the electron. This can also go via excited states, and for example, in O2, is quite notorious for having 1 meter stable state, which quite efficiently strips the electrons of O minus. And again, you see whether we include the states of this reaction can make here quite a significant difference in the number of negative ions, which will then can influence again the electron temperature, and via this, for example, your neutral radical densities. So as you see, having good data on your for your reactions and including all important reactions is important to get accurate results. However, on the other hand, you also don't want your chemistry sets to grow too large. So you don't need that much computational power to run your simulations, especially if you increase your dimensionality. In a 0D model, even if you have lots of species and reactions, it might still run in maybe a few minutes at most. Whereas for 2D or 3D, it can make a difference between running for a few hours or a few days, depending on how large your so having a very large chemistry set and a kind of optimized small chemistry set for your specific process parameters. So we need to take care to get with the construction of your chemistry set. And how can you construct a chemistry set? Basically, I mean, there are kind of, I'd like to put them into two kind of more extreme approaches. One which I like to call all-in, where you simply look for all reactions and species you can find for your gas mixture, and don't just put everything in you find and run your simulation, and which has the advantage that it's kind of fast, but the disadvantage is that you lose some control of what you put in. And if you just take everything you find and then you kind of experience some problems like instabilities in your simulation, or the results just are not a good fit for experimental results, it can be hard to identify which reactions might have faulty data, or which reactions might be missing, or maybe you also have some duplicates in your chemistry set when you took different sources and put them together and such. So this approach is usually a good approach if you use gas mixtures which already have established sets and data with sufficient available data, for example, let's say argon, oxygen, or something like this. The other one is the step-by-step approach, which is a bit more careful. Basically, what you do here is that you kind of start just with the feed gas, or maybe just one of your feed gases in a mixture. Use, for example, Quantemol-C to calculate your cross sections, see which new species are created, and then go on to these species and find reactions for them. And if you have, let's say you have a fluorocarbon with an O2 mixture, you would maybe just first start with a fluorocarbon, go down this reaction chain until you reach, for example, atomic species or molecular species, which are maybe not produced that much for your process parameters, and then add the oxygen part of the set. And of course, this gives you more control. You already get an understanding of what is happening while setting up the chemistry set. It's more easy kind of to find missing reactions than if you just take everything in advance. Of course, the disadvantage is that it needs some more time. And so this is a set kind of suited if you have new gases or just some missing data. And of course, you can also combine these two. For example, for a C4F8O2 mixture or some other fluorocarbon, you might choose the step-by-step approach for the new fluorocarbon and the all-in approach for the oxygen part of your set. Of course, another question is, where do you actually get the data? Of course, there are lots of publications about it, which are scattered all over different journals and such. Of course, one answer to this question is then our very own QDB, which gives you access to cross-section and rate coefficients data for almost 30,000 plasma-relevant reactions. And it also gives you access to some pre-assembled chemistry sets and tools to automatically generate chemistry sets for specific gas mixtures and optimize them. And at this point, then I'll change to the actual website. So this is the website. And as Emma already said, you can sign up for free. So if you go to the page, there will be a sign up button instead of the logout button here. And then you can get on and look for your data. And with a free account, you already have access to lots of data. For example, if you're searching for a specific reaction, you can go here to the reaction search. And let's say you want to construct a set with CHF3 as a feed gas. Then you can, for example, enter here CHF3, say you want it only as a reactant. And if you click search, you then get here a list of all reactions in QDB which have CHF3 as a reactant. You see we have here a mixture of electron collisions and heavy particle reactions. You can also filter a bit more. For example, if you're only interested in neutral dissociation, you can choose here electron impact dissociation, and you will only get the impact dissociation reactions for CHF3 as a reactant. And then you can, for example, click here on such a reaction, and you will then get here a plot of the cross-section we have in the database, or for some we have actually multiple data sets. So then you might see all different cross-sections we have for one specific reaction. You have the reference, and you can also download the cross-section. You can also do this with the free accounts, but as Anna said, there is this limit to 20 cross-sections in a 30-day period. And you also kind of, if you have cross-sections, you also kind of find here Arrhenius parameters, which were derived assuming a Maxwellian energy distribution. Whereas for reactions for which we have only rate coefficients, you of course then will not have a plot of the cross sections, but simply directly this rate coefficient data. And of course, this way you can kind of then work yourself through the database. For example, you see that neutral dissociation of, you can, for example, then start with just the electron collisions of CHF3, then see a neutral dissociation creates F in CHF2, for example, and then you can go on and do the next search for CHF2 and atomic F, and then add these reactions to your database. And of course, if you do this here via this browser, this is faster than if you would manually find all the papers you on these molecules or atoms, but it still takes some time. And so in order to speed this up a bit, first of all, we have here a list of pre-assembled chemistry sets for some common used gas mixtures. And yeah, for some chemistry sets, you can click here. You might find here some example results we did ourselves with various simulation software, so you can check whether this gives you the results you intend to. If you have a Gold account, you can download this set in different formats, which can, for example, then be directly used in some simulation software like COMSOL or CFD-ACE Plus or BISGLO. And online, you can then also run a Boltzmann solver. This again is available with a free account, which then gives you the electron energy distribution functions for some cases and the resulting rate coefficients, for example. And also online, you can run this Fluor global model where you can enter here your process parameters. And as a result, you get then the density, so you can maybe do a quick check whether this set is suitable for your process parameters. Also do some investigations, for example, some parameter variations online. And again, this is available with the free accounts. Now, if you, one thing, of course, this list is limited, so you might not find the gas mixture you're looking for, or the pre-assembled set we have is kind of optimized for parameter range, which is outside of the one you want to look into. And so we also have this dynamic chemistry generator, where you can, for example, start with selecting your feed gases. Let's say, for example, I want an SF6, NF3, O2 mixture, and then you can click update, and then in the background, it will go through the database and starting from these feed gases, find all the reactions and species which can originate from these initial gases. And then you can choose here your species reactions. This usually takes a while, so I'm not going to do this live now. So you can choose which species and reactions you want to include, and in the again then download it in different formats to use in your multi-dimensional simulations. And again, you can run here the Boltzmann solver and the global model online. And again, the downloads are only available with Gold accounts, but the Boltzmann solver and global model for these dynamic chemistry sets are also available for free accounts. So this is how you can use QDB via the website to find your data for a specific chemistry set and run some test simulations before you put them into, for example, your multidimensional simulations. Yeah, now at some point, we want to still include some more features for the chemistry generator and the global model, but we kind of noticed that it will be, well, that this browser environment is not really suitable to do this. So what we've added and what you get with the Gold account is this desktop app, which is available for Windows and various Linux distributions. And essentially it does the same as the online generator or the online pre-assembled sets. So you can choose here one of the pre-assembled sets or choose here your feed gases. Then it connects to QDB, downloads the data from QDB. But after that, everything you do is done on your local machine, which is a bit faster since you don't constantly have to connect to the server. And creating this desktop, we also have more options for new features. For example, I here preloaded an N2H2 set. And then you get here again a list of your species, which were found in QDB. And your reactions, so you can then here select, deselect which species and which reactions you want to include. You also have here some filtering options, so you can quickly have a look at just all the positive ions, for example, and same with the reactions. And what you can do, for example, in this desktop app, what you cannot do in the browser version is, for example, that you can change your rate coefficient, the rate coefficients for the reactions. You can add your own species in case you want to investigate a gas which is not covered by QDB, or your own reactions, which may not be in QDB. So you can use this to kind of set up your own sets for gases, which you kind of just start to investigate. And how you can do this, for example, let's say you want to investigate a new fluorocarbon. You can, for example, then start with generating a CF4 set. So you get all the data in QDB for the smaller CF radicals and atomic F, for example, and then use this at your species and reaction options to add your fluorocarbons, which are maybe not in QDB. And so you can set up your set here, and then you can save it so in a native format, so you can later reload it, or again you can export it for these different simulation tools. But as I've said before, you usually or quite often actually don't want all the data in your set, especially not for multidimensional simulations, but you rather want the smallest possible set, which still recreates specific plasma parameters accurately compared to the full set. And then again, you can go ahead and, for example, run the Boltzmann solver to check whether everything is okay. And what you get out of here are electron energy distribution functions for different values of the reduced electric field. You get the rate coefficients derived from these distribution functions or the collisional energy losses. Also transport parameters like mobility, diffusion coefficient. And so you can do some investigations on it, check if everything's amiss. And you can also export them into CSV files and then maybe use them in different simulation softwares. But mostly what this is actually for is a setup for the global model, which is, in the background, it's the same global model as the online version. You can again set here your operating parameters like pressure, power, geometrical factors, assuming cylindrical geometry, your gas flows. And one thing, you can also set up your pulse power. So what you can set up here is kind of a alternating between two different power levels. And what you can also do here, what you cannot do in the web browser version, is you can set up automated parameter variations. For example, let's say you want to vary the power from maybe 100 to 500 watts in, let's say, 5 steps. So you can set up here your parameters, And then you can check here how long you want to integrate. I mean, this 1 second is a kind of standard because this is usually long enough for almost everything to converge. But sometimes when you have very complicated gas mixtures, you might need to increase it a bit, or you might want to set it a bit smaller to save some time. And now from the new version on, which we are currently still testing and which we will release in maybe the end of this month, early November, you can also optionally include a self-consistent gas temperature calculation, where you then also need to set the gas temperature, and you can optionally use the rate coefficients from the Boltzmann solver instead of ones derived from Maxwellians, which usually gives you more accurate electron temperatures, for example. And I mean, it does not simply just take the results here, but it also kind of updates it every now and then to adjust the Boltzmann solver to maybe different neutral densities. So you can set up here cases and run them. And I have here an advanced here, parameter variation for this N2H2 set. And you can, for example, check here how these different plasma parameters vary as a function of the power. For parameter variation, you can also have a look at the reaction rates and see how they differ. You can also go here to the single cases, and then you have some shortcuts. For example, you can quickly plot all neutrals, and so it doesn't get too full. You can check here how many actually displayed. And the same for reaction rates. For example, if you want to see what does actually create, let's say NH as an important radical, you can quickly plot here all the reactions which produce these particles. So this again, you can use then this global model to test your chemistry set, to see if it accurately predicts what you're expecting, if particle densities are accurately predicted for your process parameters. Because you can do it also, do some investigations with this. And you can also kind of try and optimize a bit. For example, if you check, for example, if you go back here and plot here all neutrals, and then you might see, oh, here N2H2, N2H3 are very small. Maybe I don't need them for my under my process parameters. Can go back to the chemistry set, remove them, maybe rerun it to check that it really doesn't influence the densities of, for example, NH or NH2. So you can do this way kind of manually. Again, this is a bit of long or time-consuming task. So again, in the newest update, which will be out in 2 or 3 weeks, let's say, we added also some tools which help you to do kind of optimize your set for specific process parameters without you having to do it completely manually, like manually removing species and such. And the first tool we have here is called species ranking, which basically shows you which species mostly influence the density of another species. For example, I can choose here NH as a test species. You can then select here at which times you want to evaluate the reaction network. We have here some presets, but you can also manually select them. For example, you can then, where is it? Okay, I have to check this. You can enter manually here some values. For example, if you have pulse discharges, and yeah, as I said, then in just a second or so, you get here this results, which shows well, how species influence, in this case, the density of NH. And you see here, for example, that it's mostly NH3 and H, which are important, have an important influence on the density of NH. And you can use this then, for example, for some maybe superficial reduction. You see, you can, for example, you scroll down and see here, all these species all don't influence the density of my target species very much. So maybe I can leave them out of the simulation. So you can use this for some, let's say, superficial reduction. However, you have to be a bit careful because this analysis only takes kind of direct production and consumption of species into account. But as we see in one of the slides, for example, excitation actually influences electron density and such via electron energy losses, and this is not taken into account here. So for excited states, they might be low ranking because they don't directly produce the species, but they might still be important via the energy losses. And also, if you have more than one target species, it becomes a bit unreliable. So this gives you a rough overview over which species are important. You can use it for some maybe superficial reduction, but it becomes less accurate the more target species you have, and is especially somewhat inaccurate for excited states. So for this, then we have also the option complete reduction, which has a similar setup as the species ranking. So you again can choose here your species, the target species, let's say NH, NH2, NH3, and then maybe also electron density and electron temperature. Again, you can select your target times, where here the steady state. This is usually enough if you have continuous wave discharges, whereas for pulse discharges, you might want to use the manual selection and select one point in time during the on phase, one during the off phase. You can specify here the error you want to allow in your selected parameters, for example, 10%. If you then click run reduction, then it will find kind of the smallest possible set with regards to species, which still reproduces the density of these target species and these target parameters within 10%. And now, since this usually takes a while, I won't run this live, but to show you what you can get as a result. For example, if you have just a single run, you get then here a list of the species which could be removed, and here the species which were kept. And you can then also plot here how large the error which is caused by removing one species is, so you can maybe get a bit informed decision on which species want to be removed. And what you actually see is what I mentioned before. This is N2 star, so the excited metastable states of N2 are actually very low ranking because they don't directly produce these species, but removing it actually produces a quite large error, presumably because there is an important energy loss channel, and removing the species will then simply remove an important electron energy loss channel. But however, you see for the most other species, this ranking was actually quite accurate. So with the exception of this N2 star, this pretty much follows the ranking. And then you could, for example, go back to your chemistry tab, remove the species here, and then export it to COMSOL or VSCLOR format and such. So this is for a single run. You can also do this for a parameter variation, where you can then get these plots or this information for each single run. You can also get this overview, which has this color coding, which immediately tells you whether a species was successfully removed or not. And you see if everything is green, you say, okay, I can ignore the species for my entire parameter range. If the majority is red, probably not. And then you have some cases, for example, here H3+, which is green for all but one case, and here it's only just above your threshold of 10%. So you might say, okay, it's still okay to leave this out. Whereas you have this N2H4, which is also green for all but one case, but here you have then almost 20% difference. So you decide, okay, even if it's just one case, I might want to let it in because in this case, this error is quite large. And as I said, this way you can then reduce your sets for a specific parameter range, make the changes in the chemistry tab, and then export it to COMSOL, VSCLOR, CFDS plus HPAM format and use it in your multidimensional software. Now, another part which we set up here for optimization would be surface coefficients, which are notoriously unknown, and which can vary quite a lot for the same process. And what you can do here is that you can simply run a variation. What we do in our model is that we have, if you go to chemistry set, we have here the sticking coefficient, which simply says how many of these species are lost upon contact with the surface. So in this case, 10% of H would be absorbed at the surfaces, and this return coefficient, which shows how many of the sticking species return as the species here. So you would have 10% of H are absorbed at surfaces, and of these 10%, 5% return as NH. And these coefficients, as I mentioned, are quite notorious for being unknown. There's not a lot of data, and even if you look at data, they often vary quite a lot because it depends on the type of surface, how kind of clean the surface is and such. So what is usually done is here that you are not kind of universal values, but rather you do some kind of calibration. And again, this tool now allows you to do this calibration automatically. You can, for example, vary here the sticking coefficient for H between 0 and 1. Or if you want to say, keep the sticking coefficient constant and just vary the return coefficient for an H, this should be the other way around, for an H produced by H, or you can vary both at once. And what you can get out of this is, for example, for perimeter variation, you can then see how, for example, this viscosity and H density varies on the value of this return coefficient. So you can see this. And you can also, if you have some experimental data, for example, you can put in here target densities for your different cases. And if you run the variation, then you will, the app will find the coefficients which best produce your target densities. For example, this is an example. These are not just more or less arbitrary target densities, but what you get then is then this, in this case, the return coefficient, which best produces your target NH densities. And for example, such a plot where you can directly see how well it is actually produced. And then again, if you have this, run this, you can go back to the chemistry set, change the surface coefficients to the ones from this calibration, and then export it to your other simulation softwares. And this is what we have currently with regards to your analysis and optimization. We still plan to add some more options, like, for example, visualizing important reaction pathways, or doing such a calibration for unknown rate coefficients, or extending it so you can vary multiple sticking coefficients at once, or monitor multiple densities at once and such. So in the end, what you want this app to be is a tool, so you can quickly collect your chemistry data and do some test simulations, and use this analysis and reduction tools to optimize it for your specific process parameters before exporting them to other simulation softwares. So this is where we are now. I'd also like to show you a bit where some upcoming features we're currently working on. One is a tool to estimate rate coefficients for heavy particle collisions, because while QDB is quite comprehensive, if you investigate new gases, at one point you will probably need some data on reactions which are not available. And to fill this data gap, I mean, what you usually do is that you kind of do estimated rate coefficients. So you look for similar reactions and use the same rate coefficient. Or again, you do such a calibration and you vary the rate coefficient until you fit, your simulation fits experimental data. And to help with this process a bit, one of our former PhD students, Martina Micinek, has developed a machine learning model to estimate these rate coefficients for heavy particle collisions of the form A plus B go to C plus D. And we are currently working on embedding this algorithm into the QDB website, and also maybe tuning the algorithm itself a bit more. And the goal is then what you will see then at some point on the website, maybe roughly, if everything goes well in a few months, maybe within the next year, is a page like this, where you can then put in here your reaction here. And then here, click, for example, submit. And what you dedicated is you will shown here the species data, which was used by the machine learning algorithm, which you can then also change if something is missing, and an estimate for the rate coefficient. So that means that this is not an ab initio calculation. This is machine learning, so it's still an estimate. But it's probably better than just the usual way of simply putting more or less arbitrary values in it, or just using the same rate coefficient as for similar reactions. So this way is a fast way to fill some data gaps you might need for your simulations. But stress, it's still an estimate. And another upcoming feature we have is about radiative processes, which can also be quite important. And the global model, our global model itself, and most other simulation models are usually capable of handling radiative processes where you just have an excited state, which then decays to ground state or maybe a different excited states. However, we do not have actually a lot of data on these in QDB. So when you generate a set, well, desktop web on a generator, you probably will not have the radiative processes, which you then still might need to add manually. And there are databases out there. For example, there's ExoMol for molecular radiative processes, or the NIST atomic spectra database for atomic radiative processes. However, they are currently in a form which is not really that suitable for plasma simulations, where you often use kind of pool states, while these databases are kind of really finely structured. So what we are currently working on is a separate database called LIDA, which contains then these lifetimes of excited states in a plasma simulation suitable format, for example, that instead of having the lifetimes of vibration states resolved rotationally, which you usually don't do in plasma simulations, then you will just have an average lifetime for the entire vibrational state. And the idea is then, while we keep this in a separate database, that there will be a link between this database and QDB or the desktop app. So in the future, these generated sets will then also contain your radiative transitions. And I think with this, I came to the end of my presentation. So thank you for listening to me.